So let's go over these. Number one, what do you guys think? No one thinks anything. Monique? 4. Why 4? What's special about group 1?
They're the most reactive.
Correct. Group 1 is the most reactive, and they only exist in compounds in nature, so you are correct. Rubidium, okay? You saw Friday, put potassium. I said lithium, and I think I put it on the computer correctly on the YouTube thing. But I think I told you lithium, or I kept saying lithium, but it was potassium. That first metal that I put in the water, that was potassium. The one that like surprised me and I dropped the thing and everything, that was potassium, not lithium. I have lithium, but we're not going to use it. So anyways, you saw how reactive they were on Friday. They're only found in compounds. All right, number 2. Why are noble gases so stable? Maddie? 8 valence electrons. Or you are 100%, wait, actually, what's 5 out of 6? What would that percentage be? 90 something? You're that percentage correct. Only 5 of them have a complete octet. All right, only 5 of them. Where's my gizmo here? And I told you that. So she's saying everything the right way. Here, over here, look over here. 1, 2, 3, 4, 5. They have their complete octet. Helium does not. Why? How come helium does not have 8 valence electrons? Marcy? It only has 2 electrons. So you are right, and I'm going to take it, and that would be good on a quiz, test, whatever. So good job. But I want you guys to give me the better answer from now on. Instead of saying it has a complete octet, I want you to say it has a full valence shell, or a complete valence shell. What does that mean? It means the last energy level in that electron configuration is full. It can't hold any more. How does helium have a full valence shell? Well, this is something you didn't know until right now. The first energy level can only hold 2 electrons. So you know how sodium is 2, 8, 1? Here's your first level, second level, third level. Your first level can only hold 2 electrons. So if this only has 2, then it's full, because the first level only holds 2. So helium is stable because it has a full valence shell, not because it has an octet, because it can't have an octet. It's just a little different there, okay? Everybody else, neon, argon, they all have a full valence shell. They also have a complete octet. It's the same for them, but that's the difference. So full valence shell, complete valence shell. All right, but good job again, Maddie. That was good. And nuclear symbol for copper. Let me erase this. So nuclear symbol for copper. Can anybody tell me what that is, or what it looks like, or what the deal is there? Nuclear symbol. Earl, what do you think?
It would have the Cu.
See you.
It would have the atomic number on the left, the bottom left.
Bottom left atomic number. What is that?
29.
29. So copper is number 29. Cu. Very good. And what goes on top?
63.546.
Except we round it. We got to round it to a whole number. So if it's 63.546, that rounds to 64 goes on top. So that's called the mass number. That's called the atomic number. So that's the nuclear symbol for copper. Questions with that? Everybody's good. Okay. Let's come on back to, I don't know how this is going to work. We're going to continue taking notes on the periodic table. All right, so we left off, I believe, talking about carbon. Yes? And what's unique about carbon? I think someone over here said it. Go ahead, Emily.
It's found in every living thing.
Yeah, every living thing has carbon, okay? Organic chemistry is a humongous part of chemistry. People spend their whole lives just on one little section of organic chemistry, doing research, finding new ways. Renewable energy actually has a lot to do with organic chemistry, which makes no sense at first, but all fossil fuels are considered part of organic chemistry. So you got to have kind of good knowledge of that if you want to figure out other ways to come up with sources of energy instead of using fossil fuels, which is burning carbon. That's essentially what it is. Anyways, organic chemistry. So think organic, think carbon. Found in all living things. I think I left off with there's 3 allotropes of carbon. I think we wrote that. I don't know. I'll write it again if we didn't. An allotrope is the same element with a different molecular structure. And I might have defined it last week a little differently. But essentially, it's taking all the atoms of carbon in one source of carbon and rearranging them so they look a little different. So I guess the best analogy I could give you is if I give you a new seating chart tomorrow. So right now, let's say each one of you is an atom of carbon. All right, and you're in a certain arrangement, okay, certain spacing, so sitting near someone, and specifically someone near you, and then I say, all right, get up, and then I move everybody around, and you're sitting in different seats. That's what an allotrope is. No one turned in anything new, okay? Slade's still Slade, Max is still Max, Mackenzie's still Mackenzie, but maybe Slade's in the back, Mackenzie's up front, maybe Max is over here. So moving the atoms around so the structure looks different, that's called an allotrope. And there's 3 different versions of carbon. The first one is diamond. Second one is graphite. Third is called buckyball. It's called Buckminster fullerene. Buckyball, Buckminster fullerene. I'm going to show you, I actually have 2 videos here of what the allotropes of carbon look like. And we're not going to watch the whole video. Hey, Pat. We're just taking notes. We had like 3 warm-up questions we did. It's all right that you missed them. You can get them from someone else if they wrote them down, but not a huge thing. We just started taking notes, and I went back and showed everybody how magnesium burns and how iodine sublimes. But you can check that out at the end of class, and I can burn magnesium real quick too. I have tons of it. So 3 allotropes of carbon: diamond, graphite, buckyball. Right now, I'm going to show you what these actually look like. So again, it's carbon atoms that are rearranged so they look different. The best way to explain this is to show you. So someone get the lights, please. Can you guys get those blinds? Oh, in fact, Friday we have a quiz on all the elements on that sheet. Rain, I don't know if I told you that. Maybe I won't need the contraption today. Stay. Stay. Ah, there we go. I'm not sure if there's sound or what. I guess there's some weird music here. It's like bad 80s music.
The first allotrope of carbon we will discuss is diamond. In the diamond structure, each carbon atom is connected to 4 other carbon atoms in a tetrahedral arrangement.
Okay, so I actually have one of those right here. So this is like the base unit of a diamond. It's called a tetrahedral shape. You have a carbon, except these are yellow, and in chemistry the yellow are hydrogen. I didn't have time to. I just grabbed it right now. So imagine these are all black. So every little atom, these are atoms. Every little sphere are carbon atoms, and they're all bonded to each other. These sticks, these lines are chemical bonds, covalent bonds actually they're called. But so that's that. This is the simplest unit of diamond. Every single atom is bonded to every other one. And what happens is this pattern repeats over and over and over, kind of like desks in a row. This repeats, but like a bazillion times. All right, because it's very, very small. We're talking about atoms. So it repeats millions and millions of times, And what it actually ends up looking like is that, okay? So that is like a super zoomed in version of what diamonds look like. That's one allotrope of carbon, okay? One allotrope of carbon. That's diamond, all right? Super strong. Diamond's very strong, and that's because of the way it is arranged. All of these are bonded to each other. And if you notice, if you hook a bunch of these together, if you can kind of see it, I think you can. What's that shape right here? Someone just said it. Yeah, hexagon, right? So the hexagons repeat over and over and over and over again, and that's very strong, okay? It's a solid. You know diamonds are solids. Particles are really packed, densely packed, tightly packed, close together, all right? So that's diamond. And they just show kind of more and more views of it. Nope. We're not going to talk about that. We're going to talk about graphite, because that's confusing. Oops. Next is graphite. Where do we find graphite? It's in this room, right here, right now. Pencils, right. Everyone always says lead, right, for those mechanical. Ran out of pencil lead. I don't know where that came from. I don't know if we did use lead a long time ago. But graphite, it's graphite.
Graphite is quite different from diamond and lungstolite. In the graphite structure, each carbon is connected to only 3 atoms. Since carbon must always form 4 bonds, one of the 3 bonds must be a double bond.
So some of this is way advanced for now, but if you look at this one here, 1, 2, 3. So it's only connected to 3 of them, okay, instead of 4. And carbon has to make 4 bonds, so it makes a double bond there. So what happens here is graphite is like these 2 folders. This folder is what you're looking at right here on the screen, and then there's another identical pattern underneath it or above it, and they kind of just hover near each other. They don't touch. So you have a sheet of carbon atoms, and the 2 sheets are hovering near each other, and what's holding them together is called a force of attraction, kind of like gravity, okay? Like the Earth, or the moon and the Earth and the sun. There's no physical connection between the moon and the Earth. There's no physical connection you can touch, but it doesn't just float away into space because it's connected because of our gravitational pull. So gravity and forces of attraction in chemistry are very similar. It helps you understand that there isn't a physical connection between these, but they're attracted to each other, kind of like gravity, okay? So graphite actually forms these sheets, and these sheets are held together with weak forces of attraction. So these sheets are hovering, and when you write with a pencil, okay, or if you were to have graphite on your finger and you could smudge it on paper or on someone's face or the wall or whatever, okay? The reason that happens is when you put pressure on these sheets, so writing on paper, let's say, what happens is that weak force between here breaks. So a sheet breaks off, and then it's on the paper. And you keep writing, another sheet breaks off, another sheet breaks off. So those sheets are easily broken from each, or ripped apart, because that hovering force there is very weak. All right, diamond, you can't write with diamond, because diamond is all held very strongly with these bonds. So it's very different. Graphite's very weak, and I think she's probably going to talk about it, but I would rather just talk about it myself and show you. There we go. That's what I'm talking about, the sheets. So you have the green, the blue, the green, the blue, and it repeats over and over and over, but there's spaces between those sheets, and that's where the weak forces of attraction are, kind of like gravity, okay? That's the concept. So there's that space. So these atoms up here and these atoms, they are attracted to each other, but again, it's weak. It's a weak force. So that's what graphite looks like. And then the last one is are called the fullerenes, or buckyball, and that's what buckyball looks like. Looks like a soccer ball, okay? There's actually 60 carbon atoms, kind of like diamond, sort of. Not diamond, graphite, sorry, because it is 1, 2, 3. This atom here is connected to 3. But instead of being in a sheet, it's curled up into a ball. So this is actually stronger than graphite because it's in a ball and there's more bonds that are connected. But that's called buckyball or Buckminster fullerene. All fullerenes kind of look like that. And I don't have it, but there's, wait, I have it over here. thought there was a better picture. Anyways, this was a poster. Actually, Adam 40 did this. Anyone in here know Adam 40? So he did this. I thought there was a picture of a nanotube on there, but he did graphene. Anyways, this is kind of a cool structure, and AP Chem, I had him research this a little bit. So those are your three allotropes of carbon: diamond, graphite, buckyball. Buckyball looks like a ball, soccer ball. Graphite has the sheets, and diamond is held together with strong bonds. So we're going to write that in our notes. I just want to make sure there wasn't anything. Just real quick, what I want to show you, these carbon nanotubes. What happens is those buckyballs can break and they form like these tubes. They're called carbon nanotubes. And I thought there was, yeah, it kind of looks like that. Okay, I thought there was a better, anyways, I guess that was it. Yeah, I mean, that's kind of what it looks like. There's this stuff called graphene. Graphene is when, if you took a pencil and shaded it on a piece of paper and took Scotch tape and put it on the shaded graphite, peeled the tape off. So you have a piece of tape, half the tape has graphite on it, half is nothing. Fold the tape on itself, then rip the tape apart. What you'll have is a single atom thick layer of graphite. That's called graphene. And what scientists have discovered is if you take that and wrap it up into a tube called nanotubes, these things are like wicked strong, really flexible, super light, and they conduct electricity. So there's a lot of applications for it. From what I understand, you know, bikes, they're talking about airplanes, cell phones, a lot of things are going to be maybe made out of this stuff because it's so light and really strong. So I'm just throwing all the stuff out there. You don't really need to know all of it. Just information, something to kind of pique your interest. I think it's kind of cool. But what do you need to know? Like for in here on test of the regents, diamond, graphite, buckyball. Okay, those are the three isotopes, and we'll write a little description of each, and then we'll move on. Lights, please. Let in my vitamin D, please. It's good for you. And then we'll finish up these notes here. All right. So diamond, very strong. Very strong. Carbons bonded to each other. And because it's very strong, it has super high melting point. High melting point. Graphite, weak forces of attraction. Hold carbon sheets near each other. But again, it's easy to break those. That's why you can write with a pencil. And then buckyball, that's the 60 carbon, we'll put soccer in quotes here, soccer ball. There's like little pentagons and hexagons. Maybe it's, no, it's all hexagons. Yeah, I think. But anyways, that's the shape, and that's how it's different than those two. All right, so that took a little while, but it was worth explaining. Couple other random facts about some random elements, and then that's going to be it for the periodic table notes. You may not have homework again, but don't worry, the rest of the week you will. All right, can I kill this here? Yes? No? All right, well, I can start talking about the next one. Let's see. Silicon's the next one I have written down. Anyone know why silicon's cool? SI? Anything? Where do we find it? In the earth. You guys all took earth science, right? Silicon's like one of the most abundant elements on the planet. Are we good now? But what I like about it is that it's found in sand and quartz. So silicon, SiO2 solid, is quartz or pure sand. When I order sand, yes, I can order sand from a chemical company, and they give me sand in a container, and this is the compound, SiO2. That's the chemical formula for sand. Okay? Very strong, like diamond. Okay? SiO2. Very strong. And that's because the silicon and carbon are very similar. They're in the same group, right? They're in the same group, so it makes sense. Most abundant on Earth. Most abundant on Earth. And it's also used in computer chips because it's a metalloid, so it has properties of both metals and non-metals, so it doesn't get quite as hot as metals, but it conducts electricity. All right, nitrogen. I want to say about 78% of the air is N2 gas. It's essential to all life. Again, this is just kind of jumping around random elements that I think certain things we should talk about. Oh, you know what? Well, okay. Oxygen. I made a mistake. Silicon's the second most. Second most. My bad. Oxygen. I don't know how I screwed that one up. Most abundant on Earth. Why? Because it's not only in the air, it's also in the water, right? Lots of water on Earth, and H2O has a lot of oxygen in it. About, I want to say 20% of the air. And that's the O2 gas that we breathe. O2 is good for us. O3 gas is not good for us. That's called ozone. O3 gas is called ozone. Don't breathe O3, you'll die. O2 is good for you. Should go on a t-shirt. No? It rhymed? O2 is good for you. Alright. Let's see. Sulfur. What do we know about sulfur? I'm not going to write it. Everyone knows. What's the one thing people think when they think sulfur? It smells terrible, right? And what color is it? Yellow. I showed you that the other day. Alright. Zirconium. I talked about zirconium with you guys, right? It's that old phrase. Blank is a girl's best friend. It's an old phrase. Blank is a girl's best friend. What? Diamonds. Diamonds are a girl's best friend. So I make a joke. Zirconium is a man's best friend. You guys know what zirconium is? Or zirconia? Cubic zirconia. Do you know what that is? What is that? Fake diamond. So you get the girls fake ones. They don't know the difference. Just kidding. Tungsten. W over there. Right here. Found in filaments. We don't need to write that. That's details. We talked about the halogens. Let's talk about hydrogen. Hydrogen. Most abundant where? Not on Earth. In the... Think bigger than the Earth. Bigger than Jupiter. Bigger than the Sun. Bigger than the solar system. Universe. Why is hydrogen the most abundant in the universe? Okay, imagine it's nighttime. We take a field trip outside. I don't know why we're here at nighttime, but we are. We go outside. And I say, all right, here's your field trip, here's your demonstration. Look straight up. That's it. What do you see? Stars. Guess what they're made of? Hydrogen. Stars are made of it. Our sun is made of hydrogen, and it's slowly being converted into helium, which doesn't burn, doesn't react, doesn't do anything. So when it's all helium, the sun says, I'm done. And then guess what? We're done. Helium. Not flammable. Why? It's stable. Group 18. A lot of kids think helium is flammable. No, it's not. Hydrogen is. Hydrogen is super flammable. I guess we can write helium. What's special about helium? You guys ever suck in some helium? Yeah. Do you guys know why that happens? It's because of the density of helium, right? So it's the lowest density of all the elements. But what it does is it tightens your vocal cords, or vocal folds, what people call them. So you have vocal cords. That's the pitch or the sound of your voice. When you inhale this, it straightens, I guess. It tightens your vocal cords, almost like if you were to tighten a guitar string or something like that. And I guess that causes the high pitch. Anyone who knows about music probably understands that more than me. But that's kind of cool. And the last thing here, did I go over the 7 diatomic elements with you guys? I did? What's the acronym? Honkobriff, right? Hydrogen, oxygen, nitrogen. I'm just going to restate that. The honkobriffs. Honkobriffs. They all get a little 2, meaning they exist in pairs. They look like this. They have 2 atoms touching. I think I showed you that the other day. Question or comment, Earl?
I was wondering if breathing in helium is bad for you.
Yes. Don't breathe in a lot of helium. But yeah, this is what all the diatomics look like. Sodium looks like that. Carbon looks like that. Helium looks like that. Just examples. But all the diatomics exist together. So 2Fs or 2Cls floating around the room. Okay? Those are the 7 diatomics. So I went through it very quick because I needed to get done with that today. We are done with the periodic table. You will have a quiz on the periodic table, not just the elements. So you do need to understand all the other stuff we talked about. Valence electrons, metallic, non-metallic, character, properties, all that good stuff. I'm going to run out of time, but that's all right. We'll just go right to the bell. Let's go over the ones in the middle, because that's the new ones on this quiz on Friday. All right, so you can pack up and pay attention at the same time. All right, anyone know what SC is? Scandium. What about TI? Titanium. ZR? That's zirconium. That's our friend. V. Vanadium. CR. Chromium. Mn. Manganese. Fe. Iron. CO. Cobalt. Ni. Nickel. Cu. Copper. Zn. Zinc. Ag. Silver. It's almost gold, right? Ag. Au is gold. Hg. Mercury. What about PT? Very, very expensive. Platinum. Platinum. W is tungsten. I think that's it for in there. And then 2 on the bottom. What's U? Uranium and Pu. Plutonium. Stinks. Max? No? Little smirk? All right. So, plutonium. All right. Anyways, Pu and U. And why is Pu outlined? Why are all these outlined here? What are those? Yeah, synthesis or synthesize. We make those in labs, right? Okay, make those. So we're running. Uranium is only it's a finite resource. Okay, it will run out. I wish we were.